Our last topic for this unit is called the variation. Variation describes a relationship between at least two quantities, and they're very specific relationships. We have different types of relationships that are called variation. One is direct variation, one is inverse variation, we have combined variation or joint variation. Our goal in this portion of this unit is to solve real problems involving all of those. There are lots of applications of all of these in the physical world. One that we are going to talk about that involves direct variation is called Hooke's law. And Hooke's law states that the force needed to stretch a spring is proportional to the distance the spring is stretched. This is written, well, F for force is, would be your equal sign, proportional to, we use a proportionality constant, which we usually use the letter K, lowercase letter K for that, to the distance the spring is stretched. So let's call X the distance stretched. And then F the force. This is used in a lot of places because there are a lot of things that have springs in them that you don't even realize. One that you may be aware of is like on your car, in the shocks and struts system, you will have a spring in there. That's what prevents your car from just continuing to, bounce. It gives it some bounce instead of when you hit a bump, it gives it some comfort there because you bounce instead of, just shocking your system or whatever. So there's that. You also will see them in like doors that have, I think of like a restaurant door that swings back and forth. That will have a spring in it. And so the force needed to push that open is going to have some constant multiple, that's what this K is, of how far you need to push it, the X. Instead of is proportional to, sometimes mathematically we'll say varies directly with. That's the direct variation. In general, we say Y varies directly as, or Y is directly proportional to X if Y equals KX, where K is that proportionality constant. It'll just be some number. And that changes depending upon the situation you're in. Like the spring, the proportionality constant for the spring in your car is different than the one on the door, because you don't want, it takes a lot more force to, like, say if you push on the hood of your car to push it down than to push a door open. When two quantities vary directly, one quantity increases as the other increases. What does the graph of this look like? Well, we are talking about Y equals KX. That is linear, right? It is linear because the exponent on both X and Y is 1. The K is a constant. K is the slope, the number in front of the X, and the Y-intercept is 0, 0, because you have nothing added on there. So the idea with direct variation is that if one variable is 0, the other one is also 0. So you're going to have something that looks like this. And depending upon what the variable is, the real life situation, you could have negative. This could continue over here in a straight line into negative values. Like temperature, for example, can go negative. I was thinking more about the, force and distance kind of thing. And depending upon your position, I guess those could be negative as well. That's a lot more physics than we're going to get into here. Let's talk about this example. The cost of a house in Florida is proportional to the size of the house. So let's just write that equation right now. Cost is proportional to the size. Do we want to use S for size? It's really important to define your variables. You could use whatever letters you want, right? They're just variables. We're keeping in mind, though, that the K is a constant number. The S, the size of the house, and the cost vary. If a 2,850 square foot house costs $182,400, then what is the cost of a 3,640 square foot house? Well, we are talking about one point here, right? We're talking about this 2850 is kind of like an ordered pair with the 182,400. We want to know the second coordinate, the dependent variable, which in this case is cost, if you have a 3,640 square foot house. So let's plug them in. We don't know the K, but we can use that first data point to find the K. I'm going to divide both sides by that 2850. So let's take 182,400 divided by 2,850, and you get 64. So my equation simplifies back to, that looks like a 5, doesn't it? That's an S. 64S, C equals 64S. Now to answer this question, we just need to plug in that 3,640 in for S, the square footage. And you get 232,960. That's dollars, right? That is the cost, or would be the cost of a 3,640 square foot house if indeed the cost of houses in Florida is proportional to the size of the house and the other piece of information is correct. Okay. All right, let's look at some examples here of things that, relationships between two variables and talk about if these do represent direct variation, meaning we're looking for a linear relationship with a y-intercept of 0. Up here, this example with the house, cost of a house compared to the size of a house of size 0 does have cost 0, right? We're ignoring like the lot idea, but if you're not buying a house, you're if you're buying a house, 0 square footage corresponds to 0 cost. That kind of makes sense to us. Okay, let's talk about this example. The amount of gas you buy in gallons and the amount of money you pay. The amount of gas you buy and the amount of money you pay. Is that direct variation? Let's call the amount of gas you buy A, and the amount of money you pay, let's say M. Maybe P would be more common for that. C for cost, whatever, doesn't really matter. What we're wondering is, can you get A equals KP or P equals KA? Really, it doesn't matter which of these you do, because it doesn't matter which order you put your variables in, because we can solve this A equals KP for P by dividing by K, and then your constants, the K's, would just be reciprocals of one another. You would have P equals 1 over KA, and so that's still a constant, right? So it doesn't really matter. Well, this, to me, I'm looking at this and thinking, okay, if that is true, what would this K be? I kind of like looking at it this way. The amount of money you pay, the number of gallons of gas you buy, this number would be the cost per gallon, which is constant, right? The cost per gallon times the number of gallons you buy will tell you the total amount of money you pay. So we can use this relationship where we have that K being the cost per gallon, and so we would say this is direct variation. Okay, the idea is that one variable goes up at this constant rate as the other one goes up. That's the idea of linear, right? B, your age and your height. Well, to me, you don't grow the same amount each year, right? Remember, if we do A equals KH, this K has to stay constant the whole, oh, that's not what we would want. We would want H equals KA. Would make more sense because your age changes sort of independently. Height depends on your age, right? But this is not constant. You may grow a lot between the age of 5 and 6, and then just a little between 6 and 7, and then a lot again between 7 and 8. You know, every kid is different, and that amount of growth is not constant. And as you age, your height stops increasing, right? It levels out at some point. So if you look at a graph of this, your height may increase, but then it levels out, and we know that at the end it's going to start like decreasing a little bit as you age. So there definitely is not this linear relationship there. Okay, so this is not direct variation. The number of lawns you mow and the amount of money you make. This is very similar to part A, where if you multiply the amount of money, the amount of money comes from the cost per lawn times the number of lawns, right? And so if this is a constant, then it's direct variation. So this one I would answer with like a maybe. If you charge the same for every lawn. But if you charge a different amount for bigger lawns and smaller lawns, then this would not be direct variation. But if you charge it's 20 bucks to mow your lawn, then that would be direct variation. Distance from a light source and the intensity of that light. Distance from a light source. Well, what happens in that situation? As you get further away from a light, so as distance goes up, the intensity of that light goes down, right? This would not be direct variation. We're looking at one variable increasing and the other decreasing. The further away you get from a light source, the less intense it is. So not direct variation. Sometimes we have direct variation with powers. Something like the area of a circle. Remember the formula for area of a circle is pi r squared, right? We say here the area of a circle varies directly with the square of the radius. The proportionality constant is pi. That's the k. That's the constant that gets multiplied times r squared to give you area of a circle. So when we say with powers here, we're talking about the fact that that is squared instead of just r. Let's do one more example here with direct variation. The weight of a great white shark varies directly as the cube of its length. Let's write the equation from that. Weight varies directly as the cube of its length. So W equals K, that proportionality constant, times L squared. A great white shark caught off Catalina Island, California, was 15 feet long. So L equals 15 corresponds to W being 2,025. Let's plug those in and see if we can figure out the K. Remember, it's a constant. So we are looking to find out what that constant is. 15 cubed is 3,375. So divide 2,025 by that number, and we get 0.6. Or if you wanted to leave that as a fraction, it would be 3/5. That means our equation that describes the weight of a great white shark would be W equals 0.6 L cubed. That K would change for possibly a different kind of shark. It may not even vary directly as the cube of the length. A different shark species might have a totally different equation that describes it. But for the great white shark, this equation could describe it based on the information we're given here. What was the weight of the 25-foot long shark in the novel Jaws, or the movie, if you're looking at that? The weight is what we want to know when length is 25 feet. So 25 cubed is 15,625. I'm going to multiply that by 0.6, and I would get weight is 9,375, and our unit here is pounds. So that's still direct variation because we have a constant times whatever it is. In this case, it's the cube of the length. We do have other types of variation that we're going to look at. I mentioned inverse variation. Let's take a little break here, just to give you a chance to understand that. And we'll come back and do a different video for the rest of the types of variation.